Welcome back. Today, we are going to tackle one of those big programming buzzwords, polymorphism. It sounds complicated, I know, but it's actually the secret sauce that makes our code incredibly flexible and, well, adaptable. Let's dive right in.
The secret to understanding this whole thing is right there in the name. It comes from Greek. Poly means many, and morph means farm. So polymorphism is literally just the idea of something having many forms. If you can just hang on to that simple concept, everything else we talk about is going to click right into place.
And here's the thing, you've almost certainly been using polymorphism for ages without even realizing it. Just think about the plus symbol. When you put two numbers around it, what does it do? It performs addition, right? But what happens when you give it two bits of text, two strings? It does something completely different. It sticks them together. Concatenation. That's one symbol, two totally different behaviors, all based on the context. That, my friends, is polymorphism in a nutshell.
Now, this isn't just some clever party trick for programming languages. It's actually a fundamental pillar of what's called object-oriented programming, or OOP. OOP is this whole philosophy of designing software by modeling real-world things as objects, each with its own properties and behaviors. And polymorphism? Well, that's what gives these objects their amazing versatility.
So, how does this actually work under the hood? Well, polymorphism really comes in two main flavors. And the biggest difference between them comes down to one simple question. When does the program decide which form to use? Is that decision made super early, before the code even runs? Or is it made late, on the fly, while the program is actually executing?
So let's start with the first type, where all the decisions are made and locked in before you even hit that run button. This is what we call compile-time polymorphism. And you'll hear a few different names for this, so don't get tripped up. Some people call it static polymorphism because the decisions are, well, static. They don't change. Or you might hear early binding, which makes sense, right? The connection, or the binding, between a function call and the code that runs is made early on by the compiler.
Okay, so the first classic example of this is something called function overloading. This is a super cool feature where you can have multiple functions with the exact same name, but they each do something a little different because they accept different kinds of inputs, or what programmers call parameters.
Let's look at some actual code to see how this works. Here we've got a class that has two functions, and notice they're both named add, but look closely. The first add function is designed to take two integers, whole numbers. The second one is set up to take two doubles, numbers with decimal points. So when the compiler sees your code and you've written add 10, 2, it instantly knows, those are integers, I need to use the first version. But if it sees add 5.3, 6.2, it says, nope, those are doubles, I'm using the second one. The decision is made right then and there, it's fast and efficient.
The second big example is operator overloading. Remember our plus sign example from the beginning? Well, this is where we, the programmers, get to make up our own rules for operators. You can take a familiar symbol like plus, minus, or multiply and literally teach it a brand new trick for how to work with your own custom-made objects.
Check this out. Here, we've created our own custom data type for handling complex numbers. Numbers that have both a real part and an imaginary part. Normally, the plus sign would have no idea what to do with these things, but look what we did. Right inside our class definition, we've overloaded the plus operator. We've written a new rule that basically says, hey, whenever you see two complex objects being added together, here's what you do. Create a new complex object, and for its real part, add the two original real parts. For its imaginary part, add the two original imaginary parts. The compiler reads that rule and knows exactly what to do. No guesswork needed.
Okay, so that's making decisions early, at compile time. But now for the other side of the coin, which is honestly where things get really powerful. This is runtime polymorphism, where the decisions are delayed until the program is actually running.
And just like before, you've got a few different names for this. You'll hear it called dynamic polymorphism, because the behavior can change dynamically as the program runs. And you'll hear late binding, because that connection between the function call and the actual code happens at the last possible second, at runtime.
So how do we achieve this? Through a concept called function overriding. This is all built on the idea of inheritance. Think of a general parent class and a more specific child class. The child class can provide its very own unique version of a function that it inherited from its parent. In the magic word, the secret ingredient that makes all of this dynamic is the keyword virtual.
Okay, let's break this down because this is the key.
We've got a base class, and it has a function called display that's marked as virtual. Then we have a derived class, the child, that provides its own display function. Now, here's where the magic happens. We create a pointer that is of the base type, but we tell it to point to an object of the derived type. So when we call the display function, which one runs, the parent's or the child's? Because display is virtual, the program doesn't decide beforehand. It waits until that exact moment in the code, looks at what the pointer is actually pointing to, sees it's a derived object, and says, okay, I'm calling the derived version. That is the power of late binding.
All right, let's put these two head-to-head so you can really see the difference. On one side, you've got compile-time polymorphism. It's static, you get it through overloading functions and operators, the compiler makes the call early, and it's super fast. On the other side, you've got runtime polymorphism. This one's dynamic, achieved with those virtual functions and overriding. The decision is made late while the program is running, and that makes it way more flexible, even if it has a tiny, tiny performance cost.
If that's still a little abstract, think of it like this. Compile-time polymorphism is like planning a road trip with a fixed, printed-out itinerary. You've planned every single turn in advance. It's incredibly efficient, you just follow the steps. But if there's an unexpected road closure, you're stuck. Runtime polymorphism, on the other hand, is like using a GPS. It waits until you're actually driving, and if it detects a traffic jam or an accident up ahead, it recalculates your route on the fly. It's way more flexible, but all that real-time thinking has a slight cost.
So, okay, we've gone through the what and the how, but we've got to ask the most important question. Why? Why do programmers bother with all this? What's the real payoff here?
The benefits are just huge. I mean, with compile-time polymorphism, we can use a single simple function name like add to work with all sorts of data. And with runtime polymorphism, we can write a piece of code that operates on a general base type. And then months later, we can add a whole new derived type we never even thought of, and the original code just works. It doesn't need to be changed. This is what leads to reusable, maintainable software that's way less risky to upgrade, which is absolutely essential for building anything big and complex.
At the end of the day, polymorphism is all about managing complexity. It lets us use one simple name, one simple interface to handle a whole bunch of different underlying forms. It's what makes our code cleaner and so much more powerful. And that kind of leaves us with one final thought to chew on. Where else could this incredible idea of one name, many forms help us simplify complexity, not just in code, but in the world around us? Thanks for tuning in.